Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're tackling a problem in the realm of thermodynamics. This is around the first law of thermodynamics, closed systems, and this is a somewhat unusual problem because we go down to minus degrees Celsius, and as we know very well, water is not liquid at that point. So the problem statement reads, a rigid vessel of 20 liters volume contains water at 90 degrees Celsius with a quality of 50%. The vessel is then cooled to minus 10 degrees Celsius. Calculate the heat transferred during the process. So this is, first class, a normal problem. We have two states. We need to find information for the second state to be able to find the heat being transferred. But minus 10 degrees Celsius is going to be slightly different because at that point our water is not liquid anymore. Okay, other things to be aware of. This is a rigid vessel, so this is password, code word to the volume does not change. The other thing to be aware is that we have the units in liters, so we can go ahead before we do anything and say the volume is 20 liters, and that is the same as 20 times 10 to the minus 3 meters cubed, right? Just off the bat so that we don't forget that later on. We are at 90 degrees Celsius and 50% quality, so, saturated mixture. Easy to grab properties on state 1, and then we cool that to minus 10. Calculate the heat transfer during the process. Okay, so what do we know about the second state? Well, we know that if this is a rigid volume and V1 does not change, then V1 and V2 are the same. No mass entered or left the system, so therefore the specific volume is the same, and therefore specific volume 1 is to be the same as specific volume 2. So we can use the specific volume plus the temperature to find out properties for this state. What else is important? If we want to find what is the heat, and by the way, I believe heat is going to be leaving, right, because we're going from a 90 degrees Celsius to minus 10. If we want to find out the heat, we can apply the first law for a closed system, which states that the change in internal energy is equal to the heat gain or lost in the work, compressed or expansion. And here, because delta V is nil and work is the integral of P dV, then we know that work is also nil. And if this is the case, then I can conclude that the change in internal energy will be equal to my heat. So to be able to solve this problem and find the heat, all you need to do is find internal energy for the initial state, 1, and internal energy for the second state, 2. Okay, so let's start with the easy part, which is 50% quality, 90 degrees Celsius. So we just go to property table. We're going for 90 Celsius. So 90 Celsius is right here. And here I'm interested in, I'm trying to decrease this a little bit. Okay, and here I'm interested in the internal energy. And I know that I am going to have a mixture of 50% of this and 50% of this. Okay, so right off the bat, I can calculate what is the internal energy for state number 1. And the other thing I'm interested in is the specific volume, because I know I'm going to need this to be able to calculate the properties for state 2. So again, 50% of this, and let's go this way, 50% of this. Okay, so let's calculate this real quick. State 1, we're going to have 376.997 for the liquid plus the quality, which is 50%, and then difference between the two of them, which is 2117. Okay, they're all in the same units, and that gives me that the internal energy for state 1 is 14.3547, and that is in kilojoules per kilogram. Okay, likewise, specific volume 1 will just be the one for the liquid plus 50% and the difference between the two. Fortunately, the table does not give me the difference, so I need to do the difference on the fly here. 2.33593 minus 36. Okay, so specific volume 1 ends up being 1.1802. That is meters cubed per kilogram. Beautiful. All right, now that I have these two things, this is what I'm going to use later. And this is what I need to be able to define the second state, because the second state is at -10. So if I go here on my table, I'm going to note that this starts at a temperature of 0.1 degrees Celsius, right? This is the very beginning of the table. So this is no good, right? And if I go to my pressure table, same thing. The very first temperature that shows up is above 0 degrees Celsius, which makes sense, right? So this is a case in which I can't use either of these tables, and I can't use the superheated table, which is kind of obvious, and I can't use the compressed fluid because this is not a compressed fluid. Here it's compressed because it's not a liquid, I should say, because it's not a liquid. So instead, I need to use a table that is not even here, which is the one for saturated ice vapor. So here we are, saturated ice vapor. Okay, so here, things make a bit more sense. So this is a table that's relating water in the form of solid ice and in the form of gas vapor, right? That's transition that occurs from sublimation, right? So from solid straight into vapor without ever crossing into liquid. Okay, and here, if I go down to -10, which is what I'm interested in, -10 is here, I can note that there's two different values for internal energy. There is one for the saturated ice, okay, which is actually a negative number, okay, and one for saturated vapor, which is a very big number, right? So the difference between the two is very substantial, okay? Now, what I need to do here is, I know this is a value that is, I know that I actually saved this before. I know my specific volume is 1.18, and I need to check whether this is a mixture between ice and vapor. And to do that, I'm going to look at this number here and notice that this is greater than the 1.18. And I'm going to look at this number here and know that this is smaller than 1.18. So definitely there is some vapor in there, or else this specific volume would have to be smaller, right? And if it's a mixture, we know we can calculate the fraction of vapor that I have by relating the 1.1802 minus the 0.001089 divided by the 467.17 minus the, once again, 001089. Now, note that, okay, the space here is very significant, and the difference here is very small. So I'm expecting this to have very, very, very little vapor, okay? And indeed, when we do this math, what we get is the amount of vapor that I have. Let me just find it. Where's my math? 0.25, right? Approximately 0.25%. So 0.25%. If you're doing this on the Rogers table, I think you get 0.23%, 0.24, something like that. All right. So again, very small number. And at this point, what we need to do is, okay, if this is the case, then I know that 25 or 0.25% of energy is coming from this big number, and the vast majority, 99 plus, is coming from this number. So if I want to know what's the internal energy on my state 2, all I need to do is once again relate the two things. So negative 354.2 plus the very small 0.25% times the difference. And the difference there is 2714.8. And note that, just, quick tip. If you're doing this on Rogers, you don't have this value here. They don't give you that value straight off the bat. You need to calculate it if you're doing the difference. And a lot of students go ahead and say, okay, so 36.7 minus 354. No, right? It's not, because it's a negative times a negative, so it needs a positive. So your difference there should be 2,700, and it cannot be the 2,000 you get by doing this. Okay, silly mistakes, but happen often. So best to call your attention than to let you fall into a trap. So this turns out to be negative 347.2. Note the following, right? In spite of having a tiny bit of vapor, and in spite of the vapor being very high energy, it's so little that the overwhelming internal energy comes from the ice, which, so the vapor barely makes a difference on the internal energy there. But when we get to this point, this is super interesting, because now I can calculate my delta U, which was the point from the start, right? And delta U is just going to be U2 minus U1. In this case, we have U2 as negative 347.2, and we have U1 as, what was our U1? I forget, we calculated before, 1435.47. So 1435.47. Okay, so this means that my difference in internal energy was 1782, negative 1782, whoops, 0.67. All in the same unit, so units are kept. Okay, and this would be it if the question did not give us the volume and ask for the heat per se, not the, quote unquote specific heat. So I could say, and this is true, right? This is, the delta U, and this is also the heat, right, being released per kilogram of mass. Okay, so we're releasing, we know the negative means it's releasing this amount of energy. But in reality, we have a very, 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 very small sample, right? Or very, very small mass. Because if you recall, our specific volume was 1.18 something, and our volume was 20 times 10 to the minus 3 meters cubed. That came from the liters. So in reality, as a reminder that specific volume is just the volume divided by the mass. If I want to find the mass, all I need to do is take the volume and divide by specific volume. So that's going to be the 20 times 10 to the minus 3 meters cubed, divided by the 1.18. What was the rest of it? 1.1802. 02, and that's meters cubed per kilogram, which will give me kilograms as an answer, and that is 0.016946. It keeps going, and that's kilograms. Okay, so a very small amount of mass indeed. And now what we can do is, okay, if I want to know what is, call it the uppercase delta U, I'm just going to take the lowercase one, specific one, multiply by this mass, and that's going to give me negative 30.2096 kilojoules. So we can go ahead and approximate that. Okay, so this is approximately minus 30.2 kilojoules. Okay, so that massive number of 1700 kilojoules per kilogram now just became a very small number of 30 kilojoules. Okay, and then last but not least, because of what we said before, right, because work is nil, delta U equals Q, and therefore Q equals negative 30.2 kilojoules as well. Okay, so don't dismiss this last step. Students love to do this, forget about it, and just end here, and they lose some marks because of that. But matter of fact is that as we're going from 90 degrees Celsius down to negative 10 degrees Celsius, we have heat being released from our system, from our water, and the amount of heat being released is 30.2 kilojoules, given that there's no change in volume in the system. All right, I hope this was useful. If it was, consider giving this video a like. If you have any questions, leave them down below in the comment section, and we'll talk soon.